Salam and good day, guys. This is the second part of the video using the same example 1. So we have the plan GP 1 over s plus 1 s plus 5. But this time we use another method to design our PID instead of using the Ziegler-Nichols tuning. Okay, firstly, please refer to the page 39 in the lecture notes. Okay, we will use this as the procedures for our PID controller. Okay, since we have the third order system, we will use the ITAE model for our design. So this model is for 5% overshoot for unit step. So we are required to have a maximum of 25% overshoot. So we need to modify a little bit the value of our third order system here. So initially we will have s plus 0.71, s plus 0.5 plus minus j1. Okay, this is the dominant poles of our desired closed loop poles location, and this is the third poles, closed loop poles. Okay, now we have our plan G 1 over s plus 1, s plus 5. Then we have our maximum overshoot is about 25%. Let's say we want the maximum peak time is 3 seconds. So we find zeta using the equations that you have learned in the time response. Okay, zeta, this is the equation for zeta. And you also have omega d. So the omega d is the distance from origin to the imaginary axis of the closed loop poles. And we have sigma d, which is the real values of the closed loop poles. So we have Tp and we have omega d. So we specified Tp equals to 3 seconds. So we can find our omega d. And then from the omega d ITAE, we have 25% overshoot, but in the ITAE models is given as 5% overshoot. Let's say we divide it by 5 for the omega d ITAE, and next we can find the omega n, which from the equation. So omega n, we can find the omega n with this equation. Next, is it correct? So we have our omega n pi over Okay, never mind. Okay, so okay, so we have all the necessary information. We skip this part. Now we determine the third poles and the real value of 4 dominant poles and its complex conjugate, and also the imaginary values for the dominant poles and its complex conjugate. Okay, so now our dominant poles is located at 2.976 plus 6.1237i. Okay, let's say our PID is KC for compensator. Gain for compensator, GC is the compensator plan. We have S plus Zi and S plus Zd over S. Okay, so our Zi is zeros for Pi and Zd is zeros for PD. And let's say we want to design for PI design, we like to cancel the plan pole at S equals to -1. So then we set the Zi is equals to 1. Okay, so it will cancel out each other. So Zi equals to 1. And next is we find the zeros angle required to make sure the dominant poles is on the root locus. So from the equation we need to have the total angle of zeros minus total angles of poles equals to 180 degrees. Okay, and using the trigonometry we can find ZD, which is now is -1.08. Okay, so now we have all the values required. So our plan values and our compensator value Zi, Zd. Let's see, we put as 10 the gain. So we fire our SISO2. We open up the stat response. Okay, so look at the put diagram here. So it is unstable loop because of the zeros is located on the right side of the S plane. So we have a root locus that on the right side of the S plane. So we need to modify these zeros. So let's say we want to place the zeros just close to the origin. So let's say here instead of we have 0.18, we want to have 0.2 for example. So now our K is too big, let's say 10. Oh, sorry, should be -0.2. Okay, now we have our, we have 11% overshoot at time 1.64. So basically it's below the maximum 25% maximum overshoot required. Yeah, it's located below the 25% region. Okay, so now we have our compensator transfer function. So now we put inside, so we have 10, -1, -0.2. Okay, so now try to check the state response for the compensated and uncompensated system. So this is the first one that we use the Ziegler-Nichols second tuning method, and then this is the compensated system that we have just made just now. So look at the difference here. Okay, we managed to reduce the overshoot from 61.8% to 11% without sacrificing the peak time. So originally we have 1.67, so our compensated system is now have 1.64 seconds. Okay, this is the original closed loop without the without the controller. Okay, so we can find the parameter of the PID using PID standard. We have KP12, TI6, and TD.8. So if we want in terms of KD and KI, we have KI equals to 2, KD equals to 10, KP remain the same, 12. Okay, next, please try yourself the example number 2 using Ziegler-Nichols tuning method and also the method that we have discussed just now. So good luck. If you have any question, please ask me. Okay, bye.